So last time I did a really good job of convincing you that ethers don't do any reactions or do very few reactions, right? There's one reaction we need to go over for straight chain ethers, and that is the substitution of ethers. Right? So for the substitution of ethers, we have the same problem we had with the substitution of alcohols, right? Which is when we had an alcohol, we wanted to add a nucleophile, right? We can't do that because hydroxide's a really bad leaving group. So if we try to add a nucleophile to an alcohol, it doesn't work because hydroxide is a bad leaving group, right? So we spent a bunch of time talking about all the different ways we could turn an alcohol into a good leaving group. Ethers have the same issue, right? If I have an ether and I want to add a nucleophile, again, this is a bad leaving group. Right, so this reaction doesn't work. So I'm stuck in the same boat. I have to turn my oxygen on my ether into a good leaving group, just like I had to do with my oxygen on my alcohol. And since it's not an alcohol, we actually have less options to do this. So we just resort to the tried and true organic 1, organic 2 solution, which is throw some acid at it, right? So we can do these substitution reactions by adding HX. So I'm going to specify for right now that we're going to use one equivalent of HX. And we will end up adding halide to one side and the alcohol, and having the alcohol be on the other side. X here can be iodide, bromine, or Cl. Normally, though, the rates are iodide is fast, then there's bromine, then there's a big gap, and there's chlorine. Chlorine's slow. So for the most part, we're going to focus on examples that use iodide and bromine. Chlorine works, but not quite as well. So we can think of this reaction as the Williamson ether synthesis, but in reverse. So if you remember the Williamson ether synthesis we went over a few days ago, you have an alcohol, you add a base, and then you add an alkyl halide, and you make an ether. This reaction is you have an ether, you add acid to it, and you get out an alcohol and an alkyl halide. So you're just basically undoing the Williamson ether synthesis. So there are kind of two sets of rules we need to have for determining the products. And those rules are based on which or what types of groups are attached to the ether oxygen. So if you have secondary, primary, or methyl groups / carbons, letters / carbons on the oxygen, right? The halide goes on the least substituted carbon. And this reaction is kind of governed by an Sn2 type mechanism. If you have a tertiary carbon, on the oxygen, the halide goes on the most substituted carbon. In this mechanism is more of an Sn1 type mechanism. So we'll do some examples and we'll do some mechanisms and go through it like that. Right, so say we have our one equivalent of, say, HI, and we're going to add, we have a primary carbon, here we have a methyl carbon, so we're going to put our halide on the least substituted carbon of the two. So we're going to make this. So this is secondary, primary, and methyl. So mechanistically, why does this happen? Right? So the same thing that we did for the alcohols, we're going to do here with the ethers, right? We have our oxygen. Its lone pairs can be protonated. Now we've made the oxygen a good leaving group, and now we have this I minus. The I minus is going to do an Sn2 reaction to knock off the leaving group, right? So if you remember the rate of Sn2 reactions, right? Methyl groups are fast, right? Methyl groups are the fastest, then primary, then secondary is a little slower, and then tertiary is slow / does not happen, right? So this iodide is looking at our protonated ether that we've drawn, and it's like, all right, which one of these carbons is easiest for me to attack? Which one's easiest to get to? The methyl one has less substituents, so the methyl one is going to be easier for me to attack. So it's going to add to this side first and break that carbon-oxygen bond. Right, so it's just a question of rate. Which one am I going to add to first? Right, so you're going to look at your molecule, say, okay, this is primary, this is secondary. I'm going to add to the primary side of my ether, so I'm going to make this halide and that alcohol. Same thing here. This side is secondary. This side is primary. So I'm going to add my iodide to the primary side. So since this is Sn2, you always end up with your halide on the least substituted carbon of your ether. Now, if you have a tertiary group on your oxygen, that's going to change your mechanism, right? So if I have a tertiary carbon, I'm going to end up with my halide on my most substituted carbon. And the reason for this is that your mechanism changes, right? The beginning is exactly the same, right? I've got my HI, my oxygen adds to my hydrogen, breaks my hydrogen iodide bond, and I get my protonated ether, my I minus. Now, because I have a tertiary carbon, before I can do an Sn2 reaction, I'm going to break my carbon-oxygen bond and generate a carbocation. Right? And then that I minus I generated when I protonated my oxygen can now come in and add to my carbocation to make the alkyl halide. So it's just you have two different mechanisms based on how easy it is to make your carbocation. If you can making a tertiary carbocation, you put your halide on the most substituted carbon. Anything else, you're going to put on the least substituted carbon. Second molecule looks like I just have a giant like E sticking off of it. Not my intent, but whatever. Or the pitchfork from Arizona State. Right, so we're going to break this bond, this bond here, right, because that carbon is tertiary. So I just want to show some other examples so you don't always just think like, well, it has to be a tert-butyl group. It's any tertiary carbon is going to get the halide. Break that bond. Seems good? So there's one class of compound that kind of breaks these rules, right? It's an easy one. So you have an aromatic ether, the oxygen always stays to the aromatic ring. So when I'm saying aromatic ethers, I'm saying an ether, I'm meaning an ether that has the oxygen bonded to the aromatic ring. So it has to be the benzene, and you have to have an oxygen coming off of it. So it has to kind of have, like, come from a phenol, right? So if I add my one equivalent of HBr, the oxygen is going to stay with the aromatic ring, and the halide is going to go to the other side. So it doesn't matter if you're dealing with like a primary carbon or if you're dealing with a tertiary carbon. Right? You're always just going to end up with oxygen stays on aromatic ring, the other carbon gets the halide, right? Because we can't do Sn2 reactions with an sp2 hybridized carbon, so with the carbon of an aromatic ring, and we can't do Sn1 reactions with those carbons either. So the two reaction mechanisms available to us to do this reaction just don't work when you have your leaving group on an aromatic ring. So you just can't ever break that carbon-oxygen bond. So you're always just stuck with the oxygen on the aromatic ring. So far, so good? All right. So for all of these examples, I've been very deliberate in saying that we're using one equivalent of the acid. So the reason is we get a different product if we use two equivalents. So we have two equivalents of HBr, let's say. Instead of making an alkyl halide and an alcohol, I'm going to make two alkyl halides. So I'm not going to have an alcohol in my product. Now, if you think about this makes sense, right? So I take my first equivalent and I do the ether reaction, right? I'm going to have my alcohol and I'm going to make my alkyl halide. Now I have a second equivalent of acid, right? And I have an alcohol. We already know what HBr does to an alcohol, right? It turns it into an alkyl halide. So the product of adding HBr to an ether gives us an alcohol which can react with HBr to give us an alkyl halide, right? So I'm making a product that can then react with my reagent. So if I have excess reagent, right, if I have 1 mole of ether and 2 moles of HBr, the first mole of HBr makes a mole of methyl bromide and a mole of ethanol. And now the extra mole of HBr I have reacts to that mole of ethanol I made to make the the ethyl oh my gosh, I can't even name stuff. The bromoethane. There we go. Right? So, if we think about the mechanism here, and there's a couple different mechanisms we have to think about, but this one in particular. Right? So we have our Br minus, it adds here, break this bond. Right. Now I have my ethanol, and now my ethanol can react with more HBr. Too many dots. Right, we make our water leaving group. The Br minus can then add. Right. So you basically are doing the ether reaction and then just tacking the alcohol reaction onto the end of it. So this mechanism is new, just learned that today. This mechanism is old, it's just an alcohol reaction mechanism that we learned like a week ago. Right. So even though the mechanism looks long, you're just kind of stitching two mechanisms together and calling it good. So if you were doing this mechanism, even though in the final product, they're both alkyl halides, they're both bromides, you'd want to make sure that you did the mechanism in such a way that you made the right alkyl halide in the right order, right? So you'd say like, oh, the rules here say I've got to make the less substituted bromide first. So you make that first and then do the other thing. If you switch it, right, it wouldn't be right because you didn't make the right bromide first, right? You added to the wrong side of the ether. So like if the mechanism on the exam, which there's going to be a mechanism on the exam, right, is, hey, put all these steps in order, right? If you put them in the wrong order, you get the right product in the end, right? You get this, but you got there in the wrong way, right? Because you didn't do them in the right order. That makes sense? So you have to make sure that you follow the rules for like, oh, I've got, secondary, primary methyl, less substitute. Oh, I have a tertiary ether, so I'm going to make the most substituted halide first. You just need to make sure you keep that straight. All right. So for the first one, both sides end up having iodides on them, right? So if you were just asked for, hey, what's the product? Iodine on each side, and you're done, right? If you're doing the mechanism, you need to remember like, oh, I have a tertiary carbon, so I'm going to make this alkyl iodide first, and then make the second one. Right, so I'm going to make the more substituted one first, and then I make the second one. So just don't forget the order. But if I just ask for, yo, what's the product? 2 iodides, you're a happy person, move on. Oh, you could definitely do one that you wouldn't have to mechanism. It could be something where like, I could say, what's the product? Or like, what's the alkyl halide? I could give you options to like pick the alkyl halide product, or I could like give both products where I'd be like, oh, hey, what are the 2 products from this reaction? So it could be just exactly like what we're doing now, but then just with like some multiple choice boxes. So which carbon is going to get the halide? A or B? A, right? So I've got a primary and a secondary, so that means I put it on the least substituted carbon, and A is least substituted. So we're going to do this guy. like that. And then here again, I have two equivalents, so both sides end up with not that, end up with an iodide. Not too bad. Let's say you add 1 billion equivalents. Think of enough zeros there. Yeah. Right? Hopefully we've all seen Austin Powers. Okay, good. Doesn't matter. The oxygen still stays on the aromatic ring. Can't take the oxygen off. So no matter how hard you try, that oxygen's like, no, I'm good, thanks.
$1 billion
equivalents.
Right? Just this, boom. It's popped up on TNT once or twice. You've seen part of it, and you have to have. No, you've never seen Austin Powers? None of the 3 Austin Powers movies? There's 3 of them. They kept making them. All right. It's dark times. Dark times. Anyway, just to prove the extreme case the oxygen stays on. All right. So that's basically the only reaction you need to know for straight chain ethers. Right? Is the only thing basically, if you throw strong acid in with them, they will break apart into an alcohol and an alkyl halide. And if you throw a lot of acid at them, they'll become 2 alkyl halides for the most part. Right? The other thing we need to talk about is how to make epoxides. And then once we've made epoxides, what we can do with them, what reactions epoxides can do. So we're going to start with the synthesis of epoxides. In case you forgot, I don't know, Wednesday. That's an epoxide. There are 2 main ways that we make epoxides. Number 1, we do Sn2 displacement reactions. We just do Sn2 reactions to close and make the ring. The second way is the oxidation is we take double bonds and we oxidize them to make the epoxide. Those are our 2 ways to make epoxides. So we're going to start out talking about the Sn2 displacement stuff, and then we're going to do the oxidation stuff at the end. All right. You need an oxygen or an alcohol and a leaving group on adjacent carbons. Great, so you need oxygen, draw like this, and then some leaving group. Then you're going to add a base. My kind of go-to base for these, for the most part, is just sodium hydride. Other things can work, but I just kind of default to sodium hydride as my go-to base for this. And that will make your epoxide. So basically, we're just doing a Williamson ether synthesis. Right? Where I'm making an O- with my base. And I've got my leaving group right beside it. And we can just come down, knock off that leaving group, and make my epoxide. Right, so one of our more common leaving groups for this is just a halide. So you can say, hey, we just saw, I've got a bromide here, add my sodium hydride, I make an epoxide. Right? You can switch that around, right? You could have your oxygen be less substituted and have your halide be more substituted. Still make an epoxide. It doesn't really matter. Where it starts to matter is when we start involving stereochemistry. Right? So let's say we have so we'll make it a chlorine. Right. Here I've got my alcohol is on a wedged bond. I'm not doing anything to the carbon-oxygen bond. All I'm doing is removing the hydrogen to make an O-. So my epoxide is going to keep the stereochemistry that the oxygen had initially, right? Because nothing happened to that carbon-oxygen bond, so I'm going to keep that stereochemistry. Now, if I switch this around and have the halogen be the group that has the stereochemistry, I'll draw it like this, it'll look nicer. Add my sodium hydride. Now I make my O-. It's awful, try again. I'll make my O-. This is still an Sn2 reaction, right? So Sn2 reactions proceed with backside attack, inversion of stereochemistry, right? So what ends up happening is we are going to attack the carbon with the halogen and invert the stereochemistry. We're going to come from behind. So now my epoxide is going to have the opposite stereochemistry of the halide I started with, because I have to proceed through backside attack. What if both the halide and the oxygen have stereochemistry? I'm glad you asked. Here, my halide and my oxygen are on opposite sides, so I can do my Sn2 reaction and I can make my epoxide. Now, if they're on the same side of this ring, I have my sodium hydride. I won't make the epoxide, right? Because there's no way my oxygen can get behind my halide to do the displacement because they're on the same side of the ring. Something else might happen. I might do an elimination. I might make another kind of ether, but I'm not going to be able to make the epoxide because it can never get on opposite sides of each other. Fair? Right, so we've seen this is going to make an epoxide. Let me reverse this around. Sorry. I specifically wouldn't make the right one. There you go. So we've seen this will make an epoxide. No big deal. This is, if you remember, a halohydrin. Right? Halohydrin is just a molecule that has an alcohol and a halide in it. We need them to be on adjacent carbons, but it's still halohydrin. Do you remember how to make halohydrins? You were all there and past. It involves water. And there's a bromine in the molecule, in the product, so they're probably a bromine. Maybe, dare I say, two of them, because that's the way bromine comes prepackaged. What would that react with? Double bond. Take a double bond, you add Br2 in water, and you make a halohydrin. Then you can take that halohydrin, add base to it, and make an epoxide. I'm a failure. It just becomes more and more clear every year. Do you remember this from Organic 1? What's Organic 1? It's like, All right. There's also another way we can do this. There's another way we can get to something very similar. And that is if we take our double bond and we turn it into a vicinal diol. How can we turn a double bond into a vicinal diol? It's literally Wednesday. Do you remember Wednesday? No, what's Wednesday? It's like, the day before Thirsty Thursday. Wednesday, you know. So you can turn, it hurts. It hurts so bad. So there are two ways you can do this. One involves something that is cold. Yes, cold and dilute KMNO4. Or you can use catalytic osmium tetroxide and hydrogen peroxide. Either one of those puts an oxygen on either side of the double bond. Now, I have two oxygens. We went over a whole bunch of ways to turn oxygens into leaving groups, right? I need to end up with an oxygen beside a leaving group. And we know how to turn oxygens into leaving groups. But I have two oxygens. I need to be able to differentiate them. So the way we do that is we use tosyl chloride. Can I erase that? Oh, nope. I can either erase the whole thing, but not that stray pen mark. Check. Okay. Tosyl chloride is big. So when it goes to react with the two alcohols, it's going to react with the alcohol that's easiest to get to. It's going to react with the least substituted alcohol. So here I've got a primary alcohol, the secondary alcohol. It's easier to get to the secondary or to the primary alcohol, right? There's less around it. So if you use tosyl chloride as a thing to make your alcohol into a leaving group, you're just going to end up now putting your tosyl group primarily or exclusively on the primary alcohol because it's easier to get to. Now I've got alcohol with leaving group. I can add my sodium hydride. I can get fair. Now there's some advantages and disadvantages to these two setups or these two processes. First, this first one here takes 2 steps, right? Gotta take my double bond, turn it into the halohydrin, then add base. This bottom route takes 3 steps. So a little bit longer, but we can actually end up getting different stereochemistries in our product depending on which of these two methods we use. So let's just see. Oop. So if we take this and we treat it with Br2 and water, because of the mechanism that you learned in Organic 1, the oxygen and the bromine have to be on opposite sides. So in the end, you're going to end up with something that looks like, say, bromine up, oxygen back, methyl group up. All right? So now, if I add sodium hydride to this, it's going to kind of react just like I have it drawn. And end up with that as my product. Right? If I use the same starting material, and then I use, say, osmium tetroxide, hydrogen peroxide, the big thing you'll notice right away is that your oxygens I'm going to do it this way. Sorry. You can yell at me. Your oxygens are on the same side, right? They're not on opposite sides. I can turn this one into a tosyl group. Okay, but I can't have these react the way they're drawn. So I'm going to have to rotate around this single bond to get the two oxygens on opposite sides. And when I do that, now when I react with tosyl with the base, and you can see up here, this ethyl group and this ethyl group are trans. They're on opposite sides of that bond. while down here, the two ethyl groups here and here are cis. They're on the same side, right? So these two different ways of getting to the same kind of setup, which is alcohol beside leaving group, because their stereochemistries are different in that addition to the double bond, you can actually get different stereochemistries of your epoxide product, right? You can end up with a situation where your groups are on opposite sides they're trans, or they can end up being cis. So I think we'll end here, and we will spend next class doing the oxidation of olefins and then additions to epoxides.